Hello, and welcome to this talk on a novice-friendly induction tactic for Lean. This project kind of grew out of a course that my supervisor Jasmin Blanchette is teaching, and for which we use Lean to teach interactive theory improving. And we noticed that our students were having quite a bit of trouble with the default Lean induction tactic, that in some of the kind of more interesting arguments by induction, so for example rule induction in the context of programming language meta theory, the induction tactic was generating some goals that were genuinely quite confusing for our students. And so I set out to implement a better, more user-friendly induction tactic, and much of this was just getting up to speed with the state of the art, so in particular Cox-dependent induction. But I noticed that that tactic also has a couple of usability issues, and addressing those is what this talk is about. I will be talking about three things in particular, starting with the simplification of induction hypothesis. So the issue here is that we are using a technique by Conor McBride to deal with some issues with the default induction tactics, with kind of goals of a specific form. And this technique by McBride works by inserting some equations in the goal. So before we do the induction, we abstract over some things, then add some equations, then we do the induction, and then we eliminate those equations again after we've done the induction. And this usually works very well. It generates very nice goals, except for one thing, and this is that these equations ending up in our induction hypothesis. So here, for example, is an induction hypothesis that we actually get in the course for one of the examples that we have our students prove. And you'll note that here is this kind of strange equation between these two things that look very similar. And this is very confusing for our students because they don't know where this equation is coming from, right? The goal before we did induction didn't have any equations in it. So why is there suddenly an equation in our induction hypothesis? And indeed, this is not easy to understand if you don't know exactly what this technique is doing, which we don't want our students to know. So we wanted a way to eliminate these equations, and it's actually in many practical cases quite easy to do so. And the process we follow is as follows. So first, we replace these variables, which were also generated by the induction tactic. We replace these with meta variables. And then we go through each of the equations that were added, in this case just one, and we do first order unification of the left-hand side of the equation and the right-hand side. And in this case, since this while here is a constructor, the first order unification realizes that for each of these meta variables there's really only one possible solution, and that is s respectively t. And now this equation has become completely trivial. The left-hand side and the right-hand side are definitionally equal, and so we can immediately remove it. And we are left with this induction hypothesis, which I think you'll agree is much nicer than this induction hypothesis. This process doesn't always work. We can't always eliminate these equations with this method, but there are enough practical applications that we thought it was worth it to include this process and give our students nice induction hypothesis as much as possible. The second problem we address is something that will be familiar to anyone who has ever done any interactive theory improving. So essentially we want to prove this lemma here, which says that given n plus n equals m plus m, we have n equals m. And now if we try to do that by introducing n and m, as one usually does with all quantified variables, and then doing induction on n, we are left with this goal. By the way, I stole the example from PS Software Foundations. We are left with this goal, which is a bit unfortunate, because the induction hypothesis here requires us to prove that n plus n equals m plus m, but this hypothesis tells us that n plus n is not, in fact, equal to m plus m. What's the issue here? Well, the issue is that we need to generalize over m. So here we had an induction hypothesis that talks about a particular m, and here when we generalize over m, we get an induction hypothesis that is more general, generalizes over all m, and now we can instantiate this induction hypothesis with the correct m, and this, lets us make progress with the proof. The issue here is not that this generalization process, sorry about that, that this generalization process would be particularly difficult. In fact, it's quite easy to do this generalization. The problem is that our students have to know and have to recognize that generalization is in fact what they need to do here. So first they need to recognize that they are stuck, which is not always trivial. Then they need to recognize that this generalization trick is what they need. And we thought, okay, there's more important things for our students to know than this. And so we built the induction tactic in a way that always generates the most general induction hypothesis possible in some sense. So essentially what the induction tactic does is it simply generalizes over all the hypotheses that we can generalize over. And this is quite effective. Of course, it sometimes leads to overly general induction hypotheses, but then our students can specialize those, and that's not the biggest problem. However, there are some corner cases, which are described in the paper. I won't talk about them here, where essentially there are hypotheses in the goal that it is useless if we generalize them. They lead to a more complicated induction hypothesis that is not, in fact, more general in any significant sense. And so in the paper, I also describe a way to detect these situations and avoid at least some of them heuristically. Right, and then the last problem that we address with the tactic is naming. And you might be saying, okay, that can't be such a big deal, but let me show you. So here's another lemma that we let our students prove. This is about the transitive closure of a relation. So R is an arbitrary relation. TCR is the transitive closure of this relation. And here we are proving that the transitive closure is in fact transitive. We do that by doing induction on this H1 hypothesis, and we get this goal, which I think you'll agree is a bit of a mouthful. Just because the names that Lean's induction tactic chooses are quite bad. And here's the goal with the new induction tactic, which just reads much nicer because all the names are much nicer. Now, a lot of this is just because we removed all these H1 prefixes, which is something that Cog, for example, also does. And in general, we use a lot of naming rules that also appear in other systems. However, there are also a couple of new naming rules in the system. And there's one in particular which I quite like. So here you can see, and this is the same in Cog, that we have this X and this Z in the goal, where up here we had this A and this B. And obviously that's also quite confusing for our students, right? We're proving something about A and C, and then suddenly we're proving something about X and C. So what's the relation between those? And this is essentially just a technical artifact of how the induction tactic works. But for the new induction tactic, I've devised a naming rule that essentially recognizes this situation and recognizes that the new hypothesis that was introduced here should be named A because it was named A up here as well. And essentially the mechanism to do this is to recognize that there's a special connection between this A in this index position up here and the new A that we introduced down here. Details again in the paper, of course. So these are the three things that the new induction tactic does better than state-of-the-art induction tactics. It simplifies induction hypothesis further. It automatically generalizes induction hypothesis as much as possible, although not too much. And it has some improved naming rules. Also in the paper, but not in this talk, is an evaluation of Lean 3's metaprogramming framework, because this tactic was entirely implemented in Lean 3's metaprogramming framework. And I wrote up some of the issues that I encountered with this framework. So if you want to do metaprogramming in Lean, then it might be reasonable for you to read that section as well.